Okay, and then I'm going to show my face here. All right. So today's subtopic is on electric potential and potential energy. So what is the difference between electric potential and potential energy? We have seen potential energy before, and you guys know this as U. You've learned this about, was it last semester? Yes, last semester. You learned about potential energy, which is U, or you can write it as PE. And it was related to the gravitational force. Okay, bagi saya punya tablet ni warm up, masih buruk lagi. And it was related to gravitational force. Here we have electric force. So our U is related to electric force. So it's called a potential, it's called electric potential energy. Okay. And throughout this subtopic, it will be denoted as U or PE. And you will assume that both refers to electric potential energy. Okay, so we are not talking about gravitational in this chapter. So this U and PE refers exclusively to electric potential energy in this chapter. Okay, so that is U and PE. Electric potential, it is called V. This guy is called U or PE. Okay, we will learn what is the difference between these two. Okay, after completing this chapter, you must be able to define electric potential at a point. Electric potential is V. Oops. Calculate electric potential at a point. I need to silence this. Calculate electric potential at a point due to a system of charges. If you have like a bunch of charges, what is the V at a particular point? Define and calculate the potential energy of a charge, okay, and etc. Calculate the work done. This part is a little bit confusing. I hope I can do my best to explain this and you guys can understand. Okay, moving on. So work done on a charge, positive charge. A small positive test charge at point A in a uniform electric field E. Okay, so look at this diagram. We have a small test charge. This is our test charge. Okay, that is our test charge. Okay. Kejap, kenapa banyak sangat mesej saya ni? It's distracting me. Okay, buang. Okay. Okay, so I have a test charge, a small positive test charge at a point A. So this is my initial point. Okay, I hope everyone is with me. Jangan mengantuk-ngantuk or like belika ke apa. This is very important. So my test charge is at point A. This is my initial point. And my electric field, we have learned this, electric field extends from positive to negative. Recapping, if I have positive charge here and a negative charge over here, my electric field will go this way. This is my E. Okay, it starts from the positive charge and it ends at the negative charge. Okay, so here we have our positive test charge, and this is our E direction, the electric field direction. My test charge moves in the same direction as my electric field. Okay, it's moving in the same direction. The displacement is in the same direction. So my dx is displacement. Wow, cantiknya S saya. Displacement. Way. Okay. Displacement. So dx is displacement, E is electric field. This is our test charge and this is the initial point. This is the final point. And this is our, kita panggil source charge lah. It's not a test charge. A test charge is what we are going to move. Kita can assume this dude over here is stationary. It's not going to move. So it will act as our source charge. Okay. With this situation in mind, we have a stationary source charge, which means that around this area, my electric field should be uniform. Assuming that I'm not going to infinity, assuming that there are no other charges around, the electric field around this source charge is uniform. Okay, so if I were to draw my electric field, it would look like this. Okay, so that is my E. Kita akan assume dia uniform. Okay, so but this is too ugly. Let's just remove it. Please bear in mind that the electric field is uniform and that is how it looks like. Okay, but we are going to look at it at one dimension for now. Okay, so now what have I told you? Test charge, source charge, moving from A to B. This is the displacement, and the displacement is in the same direction as our electric field. Okay, so therefore the work done on the charge by the electric field, okay, work done on the charge is equal to the electric force acting parallel. So this is our electric force acting parallel to the displacement times the displacement. Electric force acting parallel to the displacement times the displacement. Here we have E. I did not mention F for a reason. If you guys remember, the direction of E and F is the same. F, I need to use a different color. F has the same direction as E, if you guys still remember lah. F has same direction. Okay, this is not working out. F has same direction. Kenapa ni? Direction as E. Okay, both are vectors. And if you guys remember, F equals to QE. Okay, so if F is to the right, E is also to the right. F is to the left, E is also to the left. Okay, so they are two vectors. They have the same direction. The magnitude is not necessarily the same, but the direction should be the same. Okay, so if I know my E is pointing that way, my F should also be pointing in the same direction. So this is where the equation comes from. So work done, we know work done in general is force times displacement. So the work done by an electric field is the electric force acting parallel to the displacement of the charge. Sama je equation dia, F times displacement. F must be parallel. Previously, we learned about F equals to F d cosine theta. Okay, so you're wondering where did the cosine theta go? It's still there. The cosine theta is replaced by, the cosine theta is replaced by me saying that this guy should be parallel to the displacement. Cosine theta is there to make everything in parallel. The cosine theta is not included here because they are already parallel. Kita assume they are going to be parallel. So this is the limitation of this equation. Your F and your displacement should always be parallel for this equation to work. Okay, so I hope that's clear. So it's the same as work done, the regular work done, force times displacement, cosine theta, except that we have our electric force that is parallel to the displacement. Okay, dah berapa kali ulang dah. Right. So this is equal to F, we know as F is equal to QE. So F, I'm just substituting that with QEX. Delta X, your displacement is just X final minus X initial. Okay. And there's another equation for work done, which is KQQ 1 over RA minus 1 over RB. Now, the thing that you need to perhatikan, what do you say this? The thing that you need to, I want to emphasize this one. Usually when we have delta, it goes from final minus initial, right? Here, this is not delta. This is not delta. This is the equation KQQ, the first charge, maybe test charge, and this is the source charge. And RA is your initial point, RB is your final point. So yang ni equation dia terbalik. Selalunya it's final minus initial, right? Delta is always associated with final minus initial. But this equation is not about delta. This equation memang macam ni, it is found by integration. I think you don't want to know how we integrated to get this equation. So I will just give you the equation. So the equation starts with R initial minus 1 over, sorry, 1 over R initial minus 1 over R final. It's the same thing. Okay, bear in mind, so work done from A to B is KQQ over 1 over RA, point, the first point, minus 1 over RB. Okay, lama gila saya cerita pasal ni. Hope that's okay. Okay, so we can substitute W electric into work energy theorem. And again, we are going back to our last semester. Work energy theorem, if you guys remember, work done is equal to the change in KE, and we use 1 over 2 mv squared, blah, blah, blah. You know this, it's equal to 1, W equals to minus, sorry, W equals to delta KE. So we can use this and substitute into our equation. We know that it's QEX times displacement. So this can be equal to delta KE. Okay, so electric force is a conservative type of force. Therefore, it only depends on the endpoint. Maksudnya, if I have a charge and I move my charge like this, blah, 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 and it ends up over here, I am only interested to know what is the coordinate of point A, what is the coordinate of point B. I don't care about the path. I don't care if it had to travel a longer distance. I don't care if it had to travel a shorter distance. I just want to know the displacement. You guys know what displacement is, right? It's the shortest distance. So I just want to know what is the end points. Okay, so the path taken by the charge does not matter. Does it always have to stay parallel to the E? No, it does not have to stay parallel to the E. Okay, so we know E is like this. It moves like this. Don't care as long as our endpoints are still within the uniform E. Okay. Okay, moving on. So blah blah blah. Okay, as the positive charge accelerates away from the positive source charge. Okay, so this guy is moving away. It is it's moving away. It gains kinetic energy because it is accelerating. You know that light charges repel. So this guy will have the tendency to accelerate away. So as it accelerates, it will gain kinetic energy and it loses potential energy. Okay, so this is where we come into potential energy. Kinetic energy, you know this, it's easy. When you accelerate, you gain speed. But as you move away from the positive source charge where we have higher potential, you are moving away to a lower potential. So this means that you are going to lose potential energy because you are going to a lower place. Okay? So if you are going to a higher potential, then you will be gaining potential energy. But let's just focus on this example first. You are moving away from high potential, which means you are going to lose potential energy. So applying the concept, okay, that's the next slide. Okay, when a positive test charge at rest, so we start with V initial equals to 0, moves from point A to point B, which means that we have a certain velocity for our V final. Let's just say it's 10. Its potential energy decreases because why? If we gain kinetic energy, we lose potential energy. If we lose kinetic energy, we gain potential energy. This is based on the conservation of energy, where delta KE plus delta PE is equal to 0. If you gain KE, you will lose PE equals to 0. If you lose KE, you will gain PE. I cannot have my KE to increase, but my PE does not increase. This will make this value not 0. I want it to stay 0 at all times. So if my KE is increasing, my PE has to decrease. And if my PE is increasing, my KE has to decrease to keep everything to a 0. Okay? So here we can say that delta KE is equal to minus PE. Okay, so we are assuming the potential energy at point B is equal to a 0. So let's just write that. Potential energy U at B is equal to 0. U at A is equal to something. Let's just say it's 10. Don't know why I like 10. So KE plus PE is, so let's try that. So if I am gaining 10, that's not 10. Kita kena buat 1 over 2 mv squared. Kejap. If I'm gaining KE, let me say my KE is 10. Okay. Hey, apa benda tu? It's so terrible. Okay, so I want to say my KE is equal to a 10, which means that my PE is the same value, but should be negative. Okay. So KE is 10, positive. PE is negative 10. These two equal to 0. Okay. So if KE is 0, PE is also 0 to keep everything a 0. Okay. So kita akan berpaksikan this equation. Okay. Wow, that my BM sounds good. Okay, so we are going to use this equation over and over again, and we will see this in an example, right? Okay, tak ada example lagi. Kita kena teruskan lagi dengan teori. Okay, so work done on a charge positive in the same situation where E is parallel and in the same direction as the displacement. In its natural state, the positive charge has tendency to move away from the positive source charge. We know this. This dude does not like this other dude, so it's going to be repelled. The change in electric potential energy of the charge is, okay, remember tadi kita belajar W equals to QEX delta X. There was no negative sign there. Potential energy has a negative sign. That's the difference between work done versus electric potential energy. So if delta PE, if the change in electric potential energy is negative, then positive work is done. Okay, so if my PE is negative, then my work done is positive. Dia terbalik. Okay, so W tak ada negative sign. PE has the negative sign. So they are opposite in direction. Opposite in signs, not direction. They are opposite in signs. Okay. Okay, this is very, very important. Tak apa, nanti kita akan jumpa balik banyak gila kali. Okay, so again, I'm going to repeat myself. W is QEX delta X. Delta PE is negative W. Dia terbalik. Here, tulis WAB equals to minus delta PE. Okay, so boleh. Delta PE is equal to minus WAB. It's the same thing. If my PE is positive, my work done by the electric field on the charge is a negative. Okay, so another thing that we need to take note of is work done. Okay, work done. Macam pening kepala kan? Tak apa, kita slow-slow. So work done is done by electric field. Oh. Electric field. Okay, so this is, gendut lah benda ni. Ish. Okay, so electric, salah je dulu dah. I am sorry. Okay, so W is done by the electric field on the charge. Did I write this down? Positive work done by okay, ada kat sini. Okay, tak apalah. W by electric field on the charge. But when we are talking about PE, we are talking about the change in electric potential energy of the charge. Okay, so if I say, okay, the potential energy is positive, what do I mean? It means that the charge is gaining potential energy, gaining positive potential energy. If my PE is negative, the charge is losing potential energy. What is the work done by the electric field? What is the work done by the electric field on a charge that is gaining positive potential energy? Is the opposite. So the work done by the electric field on the charge is negative. Okay, so dia terbalik. And work done is by the electric field. PE is related to the charge. Okay, hope that's clear. Alright, so that tadi tu positive charge. Okay, sekejap Okay, betul. Now we're talking about negative charge. In a situation where E is parallel and in the same direction as displacement. In its natural state, the negative charge has tendency to move towards the positive source charge. Kita tahu they like each other, so this dude wants to go there, attracted. Okay, so this is in its natural tendency. So, so the change in electric potential energy of the charge is, so remember we started off with minus QEX delta X. In this case, our Q is a negative. So we put in the negative sign over here. So we are going to get a positive delta PE, assuming EX and delta X are in the same direction. Okay, assuming they are in the same direction. If EX and delta X are opposite direction, you will get a minus sign over here and changes the PE. But let's focus on when E and displacement are in the same direction and only the charge is negative. When the charge is negative, we just substitute the negative charge into our equation. We get a positive PE. Okay. If PE is positive, then negative work is done on the negative charge by the electric field to move it from A to B. Okay. Any questions? Is everyone okay? So this is like a lot of lectures, right? Okay, bear with me. Okay, so work done on a charge from infinity. Okay, so here let's see this is positive test charge. And this is our source. They have what is the natural tendency of this positive test charge? It will want to repel. It will want to repel, but here we are moving it from the infinity to the source charge. At point infinity, E is 0. Therefore, we cannot use QEX delta X equation to solve, as this equation assumes uniform E. Remember, kita cakap pasal when we use QE delta X, we are assuming the E is the same everywhere. But if we start from infinity, obviously the E from this guy cannot reach that place. Okay, so we cannot use that equation. We have to use this, the other equation that I showed you earlier, which is the work done to move charge from A to B is equal to KQQ. K is your constant, Q is the test charge, capital Q is your source charge, 1 over RA, the initial point. Whoa. This is your initial and this is your final. Remember, it is terbalik daripada delta. Delta goes final minus initial. This guy, dia memang suka terbalik. So, it starts from initial minus final. Okay, this is not delta. This is just how the equation is. Okay, but I'm trying to tell you to emphasize on it, okay? Jangan tertukar. Selalu orang tertukar kat situ. If a charge positive Q is moved from an infinite distance to a point R, kenapa ada kat situ? Okay. To a point R from charge positive Q, it means that it moves from infinity to this point R. Point R is the distance between the distance to this charge. So this is 1 over RA. We start from infinity. 1 over infinity minus 1 over R. R is your final point. So 1 over infinity is 0. Where is my pen? So this guy is a 0. We are left with KQQ dalam kurungan minus 1 over R, which means that we have a minus KQQ over R. So this is the work done to bring a charge from infinity to point R. Point R is the distance, point R is from charge, the source charge. Okay, I hope that's okay. Nanti kita cuba summarize. It's a lot, I know. Okay, with that said, now we get to go for electric potential. We were talking about potential energy. Now we are going into electric potential. The electric potential V at a point is defined as the work required against the electric field to bring a unit positive charge, blah, 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 from infinite to the point R. Sama, it's the same definition as this guy. We are bringing from infinity to point R, except that now we don't want to know what is the work done. We want to know what is the potential, electric potential. Okay, so electric potential is defined as the minus of work done to bring that charge to point R over the unit charge. Okay, so going back to our previous equation, which was minus KQQ over R, we just substitute that into this equation. Minus KQQ over R over Q. This guy cancels out, so we are left with KQ over R. Okay. So work done is in joules, Q is in C, so it's just joules per coulomb or volt or capital V. Okay. Now this equation is really nice because it's a scalar quantity. Okay, I forgot to mention, it's a scalar quantity, which means that your life is going to be easier now. Okay, your life is going to be easy because if you are moving a positive test charge towards a negative source charge, you just have to put it inside this equation and you will get the answer. Okay, contoh. Contoh. Okay. So point R, so we are moving a charge from infinity to this point. This is our point R. Let's say point R is equal to, I need to stop using 10, so let's use 20. And this is the same R, equal to 20, bring the charge from infinity. So here I'm bringing a test charge from infinity to point R, and my source charge is a positive. Here I'm bringing a test charge from infinity to point R, and my source charge is a negative. So let's do the V, the potential. So let's say this dude has a minus 10. What's the unit for the charge is coulomb. Why is my 10 like that? Looks like a corn. Okay, so 10 coulomb. This is positive 10 coulomb. Why does it look like that? Hello, cooperate with me, please. Okay, so now let's use the equation. V equals to KQ over R. Need more space. Let's use a different color now. Okay. So V, I want to know what is the V at this point R, right? Okay, I want to know what is the electric potential felt by that charge when it is at that point R. Okay, so K is 9 times 10 to the 9. If you guys forgot, please remember it. It's your constant. I mean, it will be given, but right now we need to remember it to do the examples. And Q is the big Q is our source charge. So that's a minus coulomb, minus 10 coulomb. And our R is 20. Let's just say it's meter lah. Senang. Okay, so we can say that, okay, our potential at this point R is a negative V, which makes sense. And for this guy, let's use the V equals to K constant, Q is 10, and our R is 20 juga. So this guy is a positive V. And yeah, it makes sense. So because we are moving towards a higher potential, so it's a positive V. We are moving towards a lower potential. Kenapa dia macam tu? It's moving towards a lower potential, which means that my potential is negative V. Okay, so again, positive. When going to a positive source charge, you are going to a higher potential. When you are going to a negative source charge, where you are going to a lower potential. Okay. I hope there's an exercise coming soon. Okay, we're almost there. Okay. Okay, let's do a recap first. I think like you guys are, oh my God, what are we learning? This is so hard, blah, blah, blah. Okay, it's not hard. It's just like a lot of equations. Okay. Okay, so let's do this together. Okay, I want everyone to help me, okay? So what have we learned so far? We have learned about work done. We have learned about delta PE. We have learned about, what's the equation for W? Anyone wants to try? No one wants to
Delta
try?
KE.
Sorry, Shasha?
Delta KE.
W is equal to delta KE. Okay, boleh? Okay, betul. What else?
QEX delta X.
QEX delta X. Okay, Umar, what does EX delta X mean? Why is there an X there? A small X there?
For the distance
Okay,
is final minus initial.
so this is final minus initial distance, betul. What about the E subscript X? What does the subscript X mean?
Is it electric field?
Yes, electric field. This is electric field, betul. Anyone wants to help Umar?
Is the electric field same direction as the displacement?
Yes, correct. Betul. Nak Mango, thank you. So this EX, the small subscript X, shows that it should be in the same axis. So kita assume lah, kita selalu assume our displacement is in the X axis. So our E should also be in the X axis. They must be in parallel. They can be in opposite direction, but they need to be on the same axis. For example, if my displacement is this way, my E has to be this way. My E has to be this way or this way. It cannot be perpendicular ke ada angle ke apa. This equation will not work. Okay. There's another equation to make it work. You have to add the cosine theta, but let's not cover that. Let's just remember QEX delta X, the E must be parallel to delta X. Okay. Okay, thank you, Nat Mango. So if my EX is in the same direction as my delta X, I will say that, okay, to the right is positive, right? I'm going to say EX to the right is positive. So this guy is positive. To the right, my displacement is to the right, which means that my displacement is also positive. So this guy, both are positive. Yay. What if my EX is going to the left, but my displacement is to the right? They are going in opposite direction. We can use this equation juga because they are still parallel. So going to the left, I'm going to say that's a negative EX. And going to the right is my displacement, positive delta X. This equation still stands. Okay. EX is a vector, which means that it has direction, which means that you need to take care of the direction lah. Okay. It has to be parallel. It can be opposite or in the same direction as your displacement. Okay. I hope that is clear. Okay. What else? What else? What is the relation between work done on a charge by the electric field to the potential energy associated to the charge? What's the equation?
Delta KE plus delta PE equal to 0.
Delta KE plus delta PE equals to 0, betul. What about W and PE, delta PE? What's the relationship?
W is equal to negative delta PE.
W is equal to negative delta PE, correct. So if my charge gains positive potential energy, okay, charge gains, stress ni dengan pen ni. Okay. Charge gains positive, okay, gains positive PE. That means the work done by the electric field is negative. Work done by electric field on, this is testing my patience, electric field on the charge. Okay. Hari ni dia macam lagging sorry. Okay, so kita ada W equals to positive KE. And then Umar said delta KE plus delta PE is equals to 0, which means that we can say KE is equal to minus delta PE, which means that if we gain kinetic energy, if I'm gaining speed, I am going to lose potential energy. If I'm losing speed, I come to a stop. I start with speed V, that's my initial V, and my final V is a 0. I am losing kinetic energy, which means that I need to gain potential energy to keep everything a 0 by the conservation of energy. Okay, so this is our equation. This is also our equation. Okay, remember EX and delta X has to be parallel. What else? Is there anything else that I missed? Okay, there's another one that I'm remembering. It's the weird equation where it's not exactly delta, but it looks like a delta. And I kept on saying, okay, this is not delta, blah, blah, blah. You guys remember?
W is equal to K small q, big Q, dalam kurungan 1 per RA tolak 1 per RB.
Okay, thank you, Afika. That's right. So that is K, Q, Q. One is a test charge, one is a source charge. And your 1 over R starts from the initial instead of the final minus 1 over final. Yes, 1 over the final distance. If my work done is equal to this equation, can I use it for my potential energy? Can I use it for my potential energy? That is the question. Wow, this is very, very beautiful. So can I use this same equation? Can I slightly modify it so that I can use it for PE, delta PE? Can I or can I not? Anyone?
Can.
Can. Umar, why? Umar dah hilang dah. Tak tahu kenapa. Oops.
Because delta PE is equal to W.
Because delta PE is equal to W. Not quite. You missed the negative sign. So W
yeah.
equal to minus
Sorry.
delta PE. Yes, thank you, Umar. So betul, kita boleh pakai equation ni, but dia akan terbalik lah. So delta PE is equal to KQ. Hello. KQ, Q besar. So the negative sign will make this 3 over here, RB minus 1 over RA. So dia jadi normal, equation jadi normal macam delta. Okay, so tak payah ingat equation ni, ingat this guy, you convert to PE later, delta PE. Okay, so negative sign, very, 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 very important. This negative sign, okay? You can use this equation. Whoa, don't. Okay, you can use that equation, just add the minus sign. Okay, so I hope there's an example. Okay, so I think that recap is okay. Kejap, let's see if we missed anything. Oh, V. Kita tak cakap pasal V lagi. What else did we miss? Yes, we talked about this one. Okay, about positive and negative charge. Kita tak cakap lagi pasal tu in the recap. Okay, so we have our equation W equals to QE delta X, QEX delta X. And we have our equation PE equals to minus QEX delta X. Wow. Wow. This is so ugly. Delta X. Okay, so this is our PE. This is our W. This is our PE. There's a negative sign. I can use this equation directly if I am having a positive Q or a negative Q. If I have a positive Q, assuming my EX and delta X are both positive, then my PE is a negative. If my EX and delta X are positive and my test charge is negative, then my PE will be a negative. It will be a positive, sorry. Okay, so just put the value of charge into the equation. Just use it as it is. This is the basic equation, and it applies for both positive and negative charges. Okay, kalau dia negative charge, dia akan jadi positive. Okay, so let me write that here. So this will become negative PE. Kita akan assume EX and delta X ni positive. And this will become positive delta PE. Okay, with the assumption EX and delta X are positive. Okay. V. Okay, one more. New slide. So V is the equation is the negative of the work done to bring a charge from infinity to point R over a unit charge. And then kita tahu W is equal to minus KQQ. Betul ke minus? Bukan, positif. 1 over RA minus 1 over RB. This was the equation that Afika mentioned, over Q. Okay. So now my Q can be eliminated, and my infinity is 1 over RA, right? Infinity is over here, which means that this guy goes to 0. Minus with the minus becomes positive KQ, the source charge over, KQ over R. Okay, and this equation can be used for both positive and negative charge. Boleh dua-dua. Just use it as it is. Substitute. It's a scalar quantity. So you don't have to worry about the direction. All right, so that's the summary that what we have learned so far. I hope everyone is okay and with me still. Don't sleep. So electric potential released from rest. Positive charge accelerates spontaneously from a region of high potential to low potential, right? Because positive charge always wants to go to the negative charge, right? So this guy is the lower potential. Boleh lah. And then this guy is the high potential. Okay, so we know that the positive charge will always want to be attracted to a negative charge. A negative charge is also equivalent to a lower potential. So dia akan accelerate to the right. A negative charge akan go to the positive or the higher potential. Okay, so the thing to remember here is high potential is related to positive. It's not working. Hello. Mengundang. Okay, high potential is positive, lower potential is negative. Okay, tu je kena ingat. Because you already know that like charges repel, different charges attract. So positive nak pergi ke negative, which is lower potential. Negative nak pergi positive, which is high potential. I know it seems a lot. You guys will get used to it. Kita akan buat example nanti, okay? Okay, so other forms of electric potential equation. So here we have our V, KQ over R applicable if test charge brought from infinity to charge Q at distance R. Forgot to mention that. And then delta V, this is V. Delta V is VB minus VA or V final minus V initial equals to delta PE over Q, or PE final minus PE initial over Q. Sama je. Okay, and then delta PE is also equal to minus QEX delta X minus EX delta X, the guys that should be in parallel, is equal to delta V. So this is another equation for PE. Okay, positive. How do I change it to work? Work done is equal to minus P minus delta PE, which means that if I wanted to use Q delta V, it will become Q delta V. Ni positive, ni negative, okay? You have to remember W is always equal to minus delta PE. Okay, and then it just like, you just have to memorize one equation and then just use it over and over again. Okay, please, tak ada example lagi ke? Okay, tak ada lagi. So potential is inversely proportional to the distance from the source. So kita tahu V equals to KQ over R, which means that V is inversely proportional to R. Inversely proportional, eh? So this is when V increases, sorry, when R increases, kita akan go to the right, right? When I'm going to the right, my R increases. So when my R increases, my V has to decrease. So jatuh. Okay, so just look at this equation. When R increases, V must decrease. And then sama juga, if I have a negative charge, what happens? So if I have a negative charge, this guy will become V equals to K minus Q over R. If my R increases, my V becomes, what does it become? It decreases. But it decreases in value, but it becomes, macam nak cakap? Okay, korang tahulah, ni maths je lah. Okay, so it will, the shape is the same, it's just flipped. Okay, it's flipped. How do I make this intuitive? Jap. It becomes smaller. It becomes a smaller value. It becomes a smaller negative. Sorry, it becomes a smaller value, but macam nak cakap? Susah lah cakap pasal maths ni. Okay, mula-mula dia start pada minus 1, negative minus 1. And then towards, when it reaches R equals to 6, the value of V becomes minus 0.2. Minus 0.2 is greater than minus 1. Okay, that's all I'm going to say about this. Just plot the thing, okay? I think you understand what I'm trying to say. It's just hard for me because it's math. Okay. Okay, because V is a scalar quantity, yay, we can just add it as it is. We don't have to resolve it into X and Y components like we did for force and like we did for E, for electric field. For V, you just have to know what is the potential at point 1, potential at point 2, potential at point 3. What is the equation for V? V is equal to KQ associated with the source charge over R. Jadi kita akan tengok how the equation is. Do we have it here? Yes. Okay, so the net potential at a point. So here I have positive charge Q1 and then I have a negative charge Q2. Okay, nanti we will go for a break. Jangan sabar sikit. So I want to know, hey, what is the potential at this point P? So I want to know what is VP due to the charges here. Charge here and the charge here. Because obviously if I'm at a point and there are two charges that I can see, I will obviously feel the effects of both charges, right? So I need to know, okay, what is the effect of this guy on me? What is the effect of this guy on me? So VP will be equal to V1 and V2. What is V1 and what is V2? Kita tahu the equation is V equals to KQ over R. So V1 is KQ1 over R1, the distance from the charge to the point that we are interested in. V2 is equal to KQ2, the charge that I'm interested, the charge that will be affecting me over the distance of the charge to the point that I'm interested in. And then we just add V1 and V2. Here, the Q2 is negative, so they are saying this guy should be negative. So V1 minus V2 will give you the net potential at point P. So this is ada happy ending lah. Ni macam senang sikit. Okay. Okay, one more. Nanti kita wait. Okay, ni panjang. Okay, let's have our break. I know everyone's like dying. So let's take a 7-minute break. Come back at 12:05. Okay, if you have any questions, you can ask me now, or if not, just take your break. Okay. And if you have not signed in your attendance, please do so. Bila kita nak ada example ni? Jauhnya.
Doktor,
Yep. Okay, almost there. Yep. Fakri.
saya nak tanya soalan dalam YouTube yang Doktor share itu. Tak silap saya example 16.1.
Sampai
Dal-
16.1. Sekejap. 16.1. This one?
Bukan jauh lah pula. Dia yang kena tentukan direction of the thing.
Sekejap Yang ni ke? Macam mana gambar dia? Saya tak ingat dah lah. Do you remember the figure? Is it this one? Oh, this is not an example. Sekejap. Is it this one?
Not this one.
Is it electric
Sikit.
field or force?
I get to you back, Doktor. Sekejap.
Okay.
Doktor, dalam YouTube ni dia cakap soalan 16.1 exercise 16.1.
Oh, exercise. Sekejap Oh, it's this one. Okay.
Ya, actually bila saya kira saya dapat kan jawapan dia kata right word kan. Tapi yang doktor bagi dalam video doktor left word. So saya macam mana dapat left word.
Saya silap kot. Sekejap.
So what is
Ada orang cakap ke? Saya tak dengar. No one? Okay. So this one, 3-point charges along x-axis shown below. Calculate the magnitude and direction of the total electrostatic force exerted on Q1. So Q1 ada dua force. One is associated from Q2, one is Q3. Q3 akan repel. So this is F3. This is F2 attracted. F12, F13. Okay, lepas tu F12 KQQ R over R squared. F12 is 9, 12, micro 20. This guy should be negative. Oh, this is magnitude je. Okay, so F magnitude. So the magnitude is F12 kita tahu direction dia positive to the right. Okay, F13 KQ1 Okay, Q3 over R squared 0.32. Okay. Leftward. F13, leftward. Okay. 150 tolak. 37.97 is to the right. Saya jawab to the left Kenapa Tak ingat lah kenapa. Why did I say
sebab
it was to the left? Did I say
calculation rightward tu doktor letak negative 150.
Oh, okay. Okay, this equation only for magnitude. Maybe saya silap kat situ. So we determine, so it shouldn't be negative minus 150 lah. It should be it should be always positive. It's a magnitude. Then, saya silap. Nanti saya betulkan. Thank you, Fakri.
Welcome doktor.
Okay. Correct myself. Exercise 16.1. So should be to the right. Okay, is it time yet? No, not yet. Okay, 1 more minute. Okay. Hmm. Okay, it's time. I hope everyone's back and feeling a little bit better. Okay, so we are going to continue with equipotential points. What are equipotential points? It is actually potential, but potential that are equal. So it's equal potential. So that is what equipotential mean, equipotential. Okay, so it means that if there's a dotted line connecting like this, it means that for this entire circle, the V is the same. If the V is 10, all points on this dotted line is equal to 10. So if I say, okay, what is the V at this point? Wow, my circle. Okay, so going closer to a positive source charge, I will go to a higher potential. My V should be bigger. So if this guy is 10, maybe this guy should be 12 volt. Okay, so going closer towards a positive source charge, I am going towards a higher potential, which means that my potential will increase, right? So along this dotted line, everywhere I go, let's say I want to place my positive test charge over here, I am placing at a potential of 12 volt. If I place my test charge over here, I am placing my test charge, hilang pula dah. I am placing my test charge at 10 volt if I'm placing it here. Kejap. Tiba-tiba pula jadi macam ni. Okay, it's good. So positive. Kalau if I place it here, I'm still placing it at a potential of 10. If I place it here, I'm still placing my test charge at a potential of 10. If I place my test charge over here, I'm placing my test charge at a potential of 12. So along those lines, the potential is the same. It depends on the distance from the source charge. So let's see. It depends on the distance from the source charge. Remember, our equation is V equals to KQ over R. If my R is if my R is further away from the source charge, which means that my R is increasing, my V decreases. Which means that if my test charge is placed further away, this is R, this V should be less than 10, should be less than 12. Let's say it's 5 volt. As it goes away from the positive source charge, the V becomes smaller based on this equation. Okay. Equipotential means around that radius, the potential is the same. Now, I said my test charge is placed like R equals to 15 meter away from the source charge. So the radius of 15 meter from the source charge all have the same potential of 5 volt. Doesn't matter if I'm here, doesn't matter if I'm here. The voltage, the potential is the same. Potential, equipotential, the potential is the same. Yang membezakan is radius, right? Based on this equation. Okay. So it's the same case for a negative potential, for a negative charge. So we know that the potential is equal to KQ over R. If I have a negative charge, then my V is a negative. So going towards the negative source charge, I am going to have a more negative V, and going away from the source charge, I am going to have a less negative V. Don't know how to, what's the right word to say? Tak tahulah. Okay, more negative, less negative. I hope that's the right way to pronounce, the right way to describe it. Okay, so it depends on the R. So moving away, the value becomes smaller or become less negative. Going closer to the source charge, going closer to the negative source charge gets more negative. Okay. And sama juga like the positive source charge, we have at a certain radius, the potential is the same. So this is the same, this is potential the same, potential is the same. If it's 5 volt over here, it's 5 volt over there. Okay, along those lines, same radius, same volt. That's equipotential. Okay, so here they are showing to you different equipotential lines. So this is an equipotential line, first, second, third, fourth, and it's saying we start off with high, and then as we move away from the source charge, it goes to a low V. Okay, we talked about this. So let's talk about V1. V1 is KQ, it's the same source charge. The R is just R. Okay, then V2, this is our V2, this is the R over here. So it's 2R, it's twice the distance compared to R. So it's 2R, KQ, same Q, you don't have to change the Q, over 2R. So it's half the volt that I got over here. So as you go further away, the voltage the potential becomes less. Okay, so V3, same thing. Now the distance is 3 times the original, 3 times the distance. So KQ over 3R, so it's 1 over 3 V1, okay, and so on. So V1 is greater than V2, greater than V3, greater than V4. So same case for negative. V1, we go for the most negative, which is, yeah, this one is the most negative. So V1 is the most negative, and then when we move up to 2R, it's half the amount of negative that we experienced earlier. I don't know how to explain this. Okay, so basically V4, we are moving towards high potential or less negative. I guess high potential is better, more negative. Okay, so we are moving from low to high. So going away from a negative charge, the V is increasing. Okay, so V4 has a greater value than V1, V2, and V3. Okay, kita balik je lah. Okay, so now we are going to talk about electric potential difference between 2 points. So we already talked about equipotential lines, and we know that along this line, the V is the same if this guy is V2, this guy is V2, this guy is V2, along those lines. So if this guy is V1, the whole area, the whole line, wherever you place your test charge along those lines is V1. Okay, so let's look at this situation over here. We have a test charge, no, electric potential difference between 2 points is given by, so we want to know what is the potential difference between V1 and V2. Okay, so delta V, V2 minus V1 is KQ over R2 because this relates to V2. It's the same charge, but our R is R2. Okay, this is the distance. Minus KQ is the same charge, but the distance is different. Okay, so this is R1. So this is delta V. Okay, so, I think this is straightforward enough. Then we have equipotential surface. Just now we talked about circle, dotted circle. Now we are talking about surface. Just imagine that if we have a positive source charge and this is our equipotential line, this is exactly the same thing. But now you imagine the source charge is like in a globe. Okay, so saya tak pandai lukis, but the concept is the same. So this is, you only care about the radius. You only care about the radius here. So this is R2, this is R1. It's exactly the same as equipotential line, except that along the surface, all the potential is the same. Previously, we talked about along the line, the potential is the same. Now we're saying, okay, along the surface, the potential is the same. Now you have to imagine in 3D. Previously, it was in 2D. Imagine the circle becomes a globe now. It becomes a sphere. So it's the same concept. All points on the surface has the same potential. Okay. Tak payah fikir penat-penat lah, macam ingat equipotential line tu sama potential je. It is only affected by R. So the further away you are from the positive charge, the lower V you have. So if you have a negative charge, moving away from a negative charge, you are actually going to a higher potential. Terbalik kan? Okay. So this is the equipotential line for a pair of negative and positive charge particles. Wait, do we have this in the book? Sekejap, I forgot to check this one. We have it. We don't have it. Okay, yeah. Okay, so we talked about equipotential lines. We talked about equipotential surface. Equipotential means equal potential, right? And equipotential line is different than electric field lines. Different, eh? This is equal potential, equal V. This is E, different. Kejap. Wait. Here you go, mommy's teaching. Nah. Hey, go downstairs. Bye-bye. Okay, sorry about that. Okay, is everyone still with me? Are you guys like sleeping? Does anyone have questions? Is everyone still alive?
Yes,
It's a bit hard. Okay, that's funny.
So,
Okay, thank God. Okay, so equipotential, same V, same potential. Electric field lines is different. So this is your E, This is your E. This is your E. This is your equipotential. There's no symbol for equipotential. It's just a dotted line. Okay? Tak ada symbol. There's no calculation involved. Okay. Tak payah. Okay. Okay, yay, thank you. So a uniform electric field of magnitude 405 Newton per coulomb, right? So we have our E, which is 405. Okay, pointing in the positive X direction. So our E is pointing this way. This is our E. X on an electron, which is initially at rest. So we have a negative charge somewhere. So let's see, assume our electric field is uniform. Okay, and our charge is a negative charge. Is that the symbol? Yes, negative E. Oh, wait, negative charge, like that. Okay, so initially it is at rest. So we know that VI is equal to 0. Okay, the electron has moved 2.8 centimeter. So delta X, we don't know the direction, but it says that it's 2.0 centimeter, or I need to convert everything to SI. I don't know the direction yet, so I'm just going to write it like that. 1, 2, 0 to 8 meter. So that is my displacement. So I start from rest. I have an electric field. So it moved with no, how do I say this? With no, tak ada orang apply lah. Okay, tak ada orang apply work to like move it. So it's going to move on its own. So when it moves on its own, it will follow its natural tendency. So natural tendency, we know that E points from high potential, positive, to negative, right? But ini untuk guidance je, you shouldn't write the charge there. For guidance, your E should go from high potential to low potential. Okay, remember your electric field lines start from a positive charge to a negative charge. Okay, so if I have a negative charge over here, the electron's tendency to move is towards the, can anyone tell me? Going to the right or to the left? I am a negative charge. I want to go to a lower potential or a higher potential?
Higher.
Higher.
I want to go to a higher. I am attracted to positive, right? Higher means positive. That's the way to remember it. So electron, my natural tendency is towards a higher potential place. Okay, so I will go to the left. So this guy, now I know the direction, it is a negative because it's going to the left. Whereas my electric field is going to the right. So I will say this is a positive. Both are vectors, so we need to put the signs. Okay, so the electron has moved. What is the work done by the field on the electron? So this is the definition of work done that we have learned so far. So what is the equation for this? W equals to the first one that we learned. What is it?
QEX
QEX
delta X.
delta X, correct. What does the EX delta X mean? What does the subscript X mean?
Same.
Parallel.
They are in parallel. Are they in parallel here? So this guy is to the
Yes.
right, this guy is to the left. They are in parallel but in opposite direction. Okay, so our Q is electron. So it's a minus, right? 1.602 times 10 to the minus 19. I think that's right. So C. So that is a minus. Remember, work done is positive QEX delta X. Yeah, for delta PE is a negative. Okay, terbalik. So EX, we know the value is to the right, so that's a positive 405 Newton per coulomb. And then I have my displacement, which is to the left, it's a vector and it has direction, 0.028 meter. Okay, so my work done is equal to, am I missing anything? Q, we have the sign for Q, we have the sign for E, we have the sign for our displacement. Okay, let's see, what is the answer? Minus 1.6405 minus. Okay, so the answer is this one. Yay, we got it. Okay, so the answer is whatever that we got just now. Alah, tak ingat. 1.82 times 10 to the minus 18. Okay, so work done is type of energy. It's a type of energy, so it is in joule. 1.82 times 10 to the minus 18 joules. Betul tak? Tak kira balik. 1.602 times 10 to the minus 19 times 405 times 0.028. 1.82 times 10 to the minus 15. Sekejap. What am I missing here? 2.8 centimeter divided by 100, 0.028. 405, 1.602. Betul ke saya punya constant ya? 1.60 times 10. Sekejap. Let me calculate again. 1.602 times 10 to the minus 19 times 405 times 0.028. Okay. Okay, dapat. So it's minus 18. This is not a triangle, it's a zero, okay? Times 10 to the minus 18 joules. So that's the work done. Easy. So Q is minus, EX is positive, and our displacement was on the opposite because it followed the natural tendency. Okay, what is the change in potential energy associated with the electron? Okay, easy. We know that W is equal to minus delta PE. If my W is equal to 1.82 times 10 to the minus 18, then my PE is equal to 1 minus 1.82. A. Okay, what is the unit? It is still joules. Okay, so semua type of energy. What is the velocity of the electron? What is the velocity of the electron? What equation should I use to solve this? What's the strategy here? Kita dah ada W, kita dah ada delta PE. How can I find the velocity? We started at rest. So VI is equal to, V initial is equal to 0. I want to know what is the V final. What equation should I use for this? How am I going to relate PE with KE? PE with KE, dah kasih hint dah tu.
0.
Equals to 0, right? Apply the conservation of energy. Okay, betul. Sekejap. Let me group this. Okay, applying the conservation of energy, we know that delta KE plus delta PE is equal to a 0. Okay, so it's equal to 0. This is the conservation of energy for electric punya thingy lah, okay? So, okay, we know what our PE is. It's minus 1.82 times 10 to the minus 18. So if I were to expand this equation, right, I will expand it like this. KE final minus KE initial, okay, plus. So do I want to expand my PE? I can. PE final minus PE initial, but I already have PE over here. So I'm just going to write it minus 1.82 times 10 to the minus 18 equals to a 0. Okay, what else? What are the other info that I have? What am I missing here?
Initially at rest.
It's initially at rest, which means that
Kinetic initial 0.
kinetic energy is equal to 0. Why is it equal to 0? What's the equation for Ke? Kinetic energy?
1/2 mv squared.
Yes, ingat lagi. 1/2 mv squared. So if my V is at rest, my Ke, initial Ke is also 0. So 1/2 M, tak kisah M apa pun. If my V is 0, everything just becomes 0. So this guy becomes a 0, so I can solve for my Ke final. Okay. Let's use blue again. So I'm going to put this on the other side. My Ke final is this guy. Positive 1.82 times 10 to the minus 18. Is this my final answer? Is Ke final equal to velocity or not? Dun dun dun, nobody knows. Is Ke final equal to V?
No.
No, the answer is no. Ke is equal to 1/2 mv final squared. Okay, so then you can solve for it. 1/2 mv final squared equals to 1.82 times 10 to the minus 18. This guy is missing one. So what is the mass for an electron? I don't know. Let's see. The mass for an electron is 9.11 times 10 to the minus 31. 9.11 times 10 to the minus 31. Okay, let's see if I can remember. So 1/2, 9.11 times 10 to the minus 31. V final squared equals 1.82 times 10 to the minus 18. Now I can solve for my VF, which is my final velocity. I hope it's right. Times 2 divided by 9.11 times 10 to the minus 31. Then square root the whole thing. You'll get, oh, this looks questionable. I don't know if it's the right answer. Let's see. I'm not going to say. Okay, betul, nasib baik. So I got 1.998902, which is 2 times 10 to the 6 meter per second. Okay, so V final equals to 2 times 10 to the 6. The unit for velocity is meter per second. We learned it in first semester. And what is the direction of velocity? Velocity is a vector. Should it go to the right or should it go to the left? I started at rest. So who should I call? Can I get, there's a name that I never called. It's Ayuni. Betul tak Ayuni? Ayuni. Tak ingat nama penawak. Is Ayuni here?
Yes, Miss.
Okay. Saya tak pernah panggil awak kan? Selalu it's Aliani Umairah. Saya selalu tertukar. So Ayuni, should my velocity, the direction be to the right or to the left?
Left.
It should go to the left. Why?
Not sure.
Not sure. Okay. If you had to guess, bantai je. Why should it go to the left?
Because
Tak apa, salah
it's
tak apa.
negative.
It's negative. Okay. Jadi,
So, I don't know, Miss.
okay.
Not sure.
Alright. Okay, thank you Ayuni for trying. Okay, so previously we talked about the condition for the electron. We said that the electron moved by 2.8 centimeter, right? And there's no force pushing it, which means that it follows its natural tendency, which means that it is going to move to a higher potential, which is going to the left. So if I started at 0, my V final is going to be somewhere on the left. Okay, so that is the answer. So it's to the left. Okay, so I hope that's okay. So Ayuni dah confused. I hope everyone else is okay. Are you guys confused about this problem? Is it hard? Susah ke tak? Ke senang? Susah lah tu, tak ada orang nak jawab tu. Okay, tak
Kena
apa.
tahu formula.
Kena tahu formula. Okay, betul. That is right. So you guys aren't used to the formula yet. Okay. So moving on to the next example. This one. Kita jawab. Okay, so this is a next example. Figure shows, what time is it? Figure shows 2-point charges Q1 and Q2 that are placed 15 centimeter apart. Okay, what is the potential difference between point A and point B? So the word here is potential, V, difference. So delta V between A and B, which means that it's VB minus VA. So this is what the question is asking. So what is this equation associated to V? V is equal to KQ over R. Okay, so if I'm looking at point A and I want to know what is the effect of this charge on point A, so I will say this is V1 KQ1 over the R from point A to Q1. So that is R1. And then for this guy, V2 KQ2 over R2, which is from A to Q2. So R2 is just 15 centimeter lah. So now let's substitute the values. So K is 9 times 10 to the 9. Q1 is positive 10 nanocoulomb minus 9 over 0.15. So that is V1. And then we have V2, 9 times 10 to the 9. And we have a negative charge minus, tak cuba tempat. Sekejap. Let's do it bawah. So now I'm just looking for V. I'm not adding anything yet. So V2 from charge 2 is 9 times 10 to the 9. The charge is negative, so just substitute the sign of the charge times 10 to the minus 9. And it is the same 0.15. Now I'm asking what is the difference between point A and point B. Okay, so I want what I'm doing here is I'm finding V1 with respect to A, V2 with respect to A. What am I finding actually? If I add V1 and V2, what am I finding? No one wants to try?
VA.
We are finding VA, betul? Correct. Thank you. So when I find V1, I'm looking at R1 with respect to A, right? So this is V1 with respect to A, this is V2 with respect to A. So if I add these two together, I will get my VA. So VA is the sum of potentials related to A, which is V1 plus V2. So that is my VA. I'm not answering the question yet. What is my VB? Now we have to do the same thing for VB. Okay, so let's do that. Nak kena kira ke tak? Kira lagi lah. Sekejap saya kira calculator sekejap. Can someone help me find V2 while I find out what is V1? 9 times 10 to the minus 9. Oh, dia opposite je. Tak payahlah, sorry. Times 10 to the 9.
600.
600. 600. So this is positive minus 600 volt. So VA, immediately we already know it's 0. Okay, so VA is a 0, which means that the potential difference between VA and VB is just VB because this dude comes to 0. So now we have to find out what is VB. Banyaknya kerja. Kejap. Let me find some courage to write. Okay, duplicate slide. Okay, let's find VB now. So how do I find VB? Tadi saya tunjuk contoh VA and it was very easy. How do I find VB? Anyone wants to try? Remember that velocity, potential is a sum. It's a sum of scalar quantities. What do I have to add to get VB? Sum of V. So I need to know what is the effect of Q1 on V. I need to know what is the effect of Q2 on V. So I have two V's going on here. So V1 with respect to B, V2 with respect to B. So V1 dengan V2 yang previously tu lain So this is V1 with respect to B, V2 with respect to B. If you want to call it V3, V4 boleh kalau tak nak confuse. Okay, so let's calculate V1. So V1, remember the equation is K Q1 over the distance between the point and the charge that we are talking about. So this is 0.05. Kita tambah teruslah. So this is VB. Okay, equals to that plus V2. So what is the effect? What is the potential felt by B from Q2, right? So K Q2 over 20 centimeter, which is 0.2. And then let's just substitute Q1. So K Q1. Q1 is positive 10 times 10 to the minus 9 plus, this is over 0.05. And this is K minus 10 times 10 to the minus 9. Tadi positif, ni negatif over 0.2. Okay. Okay, so now I can, if I want to make things easy, I can factor out the K, but malas lah. So 10 times to the minus 9 times 9 times, malasnya nak kira. Okay, can someone calculate this for me? K is 9 times 10 to the 9. K is 9 times 10 to the 9 times with this divided by 0.05. Can someone tell me what this is? This first term.
1,800.
1,800? Yeah, 1,800 volt.
Yeah.
Thank you, Nat. Next one. Someone else, please. Nasiblah korang dapat
450.
450. Okay. So this is a negative or a positive?
Negative.
Negative. Okay. So this is a negative. So now VB is 1,800 minus 450. So that is a 1350 volt. And the question is asking, what is the potential difference between point A and point B? We know that point A is 0, which means that this is 1350 minus 0, which is 1350 volt. Okay, I hope that's right. Let's see. Yay, we solved it. Okay. Is anyone confused? Let's see the solution. Is anyone confused? Do I need to repeat myself at any points? Okay, so this solution dia cakap macam ni, RA1, RA2, RB1, RB2, which is, I think this is more lagi susah nak confuse lah kot, because in my case, I immediately put in the values, right? And I said V1 and V2. Here, they distinguish the terms by this name, which is better, I think. Is anyone confused? Is everyone okay? Tambah je kan? Okay, so I'm going to assume you guys can do the web assign, okay, with for similar questions. Right, sekarang pukul 12.40, okay. Okay, itu dah habis lagi. Okay, sikit lagi, kot. Let's see. Banyak lagi tak? Can we finish this on Friday? Will it be enough time? Sekejap saya tengok. Okay, saya sambung sikit lah. Saya takut tak sempat habis on Friday nanti. Okay, sikit je. Please bear with me. Sikit lagi ni. We are almost done. I mean like 1 hour and plus almost done. Okay. So we are moving on to the next subtopic. The topic is about the charged particles in electric field. I mean, to me, the subtopic overlaps with the previous one that we learned so far, which is about W equals to minus delta PE, and V is the net charge, sorry, V is the net sum of V's, like the V at a point is the sum of V's, scalar quantity, and then we learned about W equals to minus delta PE. Then we know that W equals to KQ over R. No, 1 over RA minus 1 over RB. Okay, so these things, it overlaps with this subtopic. But I think they are making it into another subtopic so that we can like reiterate it in a different way so that you guys you guys have a better understanding of things, okay? So if it seems repetitive, because it is a little bit repetitive, right? So just bear with me. I hope it will help you to understand this topic better. Okay, so we have seen that potential V is KQ over R, right? This is the definition when we bring a charge from infinity to a point R. Remember, if we bring it from infinity, there's no E there, the V is 0, which means that we cross out something and we are left with KQ over R. We've talked about that before. And then the potential energy PE or U of a pair of charges is a pair of charges. The potential energy of a pair of charges, let's say I have this charge and this charge. So I want to know what is the potential energy of these charges. So we know that V is related to a source charge. So V is related to a source charge. Going closer to the source charge, we go to a higher potential. Going away from the source charge, we go to a lower potential. So V is associated with the source charge. If I don't want to use the word V, if I don't want to use the term V, I can say, oh, these two charges are actually interacting. So I want to know what is the potential energy. It's the same thing. So U equals to QV, or U, this is PE, basically. PE is equal to Q KQ over R, which is just V. So here Q is interacting with the source charge Q, capital Q, okay, at a distance R. So this is the distance between them, that's R. This is possibly Q, and this is the small q. And my drawing is terrible as always, but I hope you guys understand. So this is capital Q, small q, the distance between them. And if I calculate Q, K, capital Q over R, I will find out the potential energy of these two charges with the distance R, okay? So it's just another definition. So at infinity, the potential energy is 0 since electric potential is dependent on the sign of the charge particle that is given in the field. Potential energy of a charge, blah, blah, is dependent. Okay, it's just saying, just use this equation as it is. If it's a negative, then it will be a negative charge. If it is a same charge, if the pair of charges have same signs, right? For example, I have positive with positive, then this guy will be a positive. If I have a charge that is negative with negative, then the potential energy will be positive. If they have different signs, positive with negative, then my U will be negative. The potential energy associated with this pair of charges is negative. Tu je, just use the equation as it is. You don't have to like pening-pening kepala, okay? But you need to know what the equation means, okay? Okay, so we have looked at this equation before. If I remember correctly, Afika mentioned this when we were recapping. So the work done to move the charge from point A to point B or the work done by the electric field on the charge to move the charge from the initial point to the final point is equal to KQ, capital Q, dalam kurungan 1 over initial final. This is the weird equation that I talked about, right? Where RA is greater than RB. So here, RA is at a distance that is further away than RB. So if RA is further away, maksudnya RA, let's say RA is 10, RB should be smaller, maybe 7. So RA is greater, dia lagi jauh. The distance between the source charge and point RA is greater than RB. Okay, so if my RA is greater than RB, okay, so ni besar, ni kecil. Okay, let me try again. So if this guy is greater than RB, and let's say this is 1 over 10 and this is 1 over 7, 1 over 10 is 0.1. Okay, tak tahulah. 1 over 10 minus 1 over 7, that will give me a negative. So I will get a negative value for this guy. Ni contoh je tau. So RA is greater than RB. When RA is greater than RB, then my sign here is a negative. My sign for this thing is a negative. Okay. My two charges are positive. So this is positive, this is positive. So my work is negative. Okay, so what is the trick here? The trick is remembering the equation for work done or by the electric field on the charge and knowing if RA is greater than RB or if RB is greater than RA. Itu je. You just have to know if RA is greater than RB. Then just use math. Okay, so positive, positive. This guy is a negative. So you get a negative work done. Negative signs means that work done against the direction of force exerted on charge positive Q. Okay, so if my work done is negative, my PE, the gain in potential energy of the of the charge is positive. Okay, let's see this diagram. This charge is moving towards a positive charge as well. This is higher potential. Okay, the natural tendency of this charge is going away sebab dia nak repel. So this is F. But our work done is we are trying to move our charge from this point to this point. So the work done is going against the force. This is why our work done is negative. That's another way to look at it. Okay, and as we are going towards a higher potential, we can say that our final potential is greater than the initial potential. Okay, so what is important to take away from this slide? The important thing here is this equation, knowing if RA is greater than RB or vice versa. Itu je. And then just use the equation. Benda ni semua kita dah belajar before. You just have to plug it in. Okay. So the key to this topic is basically equations lah. Alright. Oh, remember that we have our work done equals to F delta X, and if they are opposite in direction, then negative work done. Which is the same case here. My F is going this way. My displacement is going this way. This is my dx. So this is why my W is negative. That's another way to look at it. Okay, but again, I'm going to remind you that the equation yang penting untuk slide ni, untuk topik ni is just this one, which is what we have learned. Okay, this is all just understanding it better. Okay, another one. The work done to follow the electric force or electric field to move charge from RA to RB. Okay, so just by guessing, I told you if force and displacement are in the same direction, then work done must be positive, right? So if they are in opposite direction, then it's a negative work done. So here, the charge is going from here to here. my natural tendency, the natural tendency of this positive charge is away from the source charge, repel. It's going to repel. So my dx, my displacement is away. My force is also away, which means that my work done should be positive. This is just a guess. Now, how do I confirm this guess? I use the equation, this equation. So positive test charge, positive source charge. Is RA greater than RB? The answer is no. RA is smaller. Now it's smaller because we start from a point that is closer to the source charge, right? So this guy is smaller, this guy is bigger. So this should be a positive, right? Yep. 1/1 minus 1/2, I get a positive, yeah. So this guy is a positive, positive, positive. So my work done is positive. Yay, our guess is correct. Okay. Use the equation to find out the actual value. Use your understanding of work done, looking at the natural tendency, looking at the displacement to see whether it's positive work done or negative work done. Or just use the equation. Okay. Right. Okay, so if I move my test charge from this point to this point, which means that I'm not changing the potential. I'm not going towards a higher potential, or I'm not going towards a lower potential. I'm moving in the same potential, which means that my UB is equal to UA. If this is A, this is point B, VA is equal to VB, right? And the equation for U is QV. If VA is equal to VB, then this guy is just VA minus QVB, which is just QVA, which is just 0. So if you move your test charge along the equipotential line, you're not changing the potential energy, you're not changing the voltage, you're not changing the potential, you're not changing the potential energy. Let me repeat myself. If you're moving along the equipotential line, you are not changing the potential, and which means that you are not changing the potential energy. No work done. Okay. So, equation ni macam salah. Sekejap, WAP minus delta PE minus UB minus UA. Terbalik. So this should be minus positive. Tak kisahlah, tapi it is equal to 0. But this equation mathematically wrong. Okay. But just know that if you're moving within the same equipotential line, there's no work done. Okay. Okay, I'm going to stop here. I'm also dying. Okay. So any questions before we end class? So we are stopping at 78. Work done on sync charges. Any questions? Everyone still alive? It's a lot, I know. Okay, so I hope everyone is okay. No one's responding. Semua jadi zombie.
If we do the activity, we'll do fine.
If we do activity, we'll do fine.
We're okay. Okay, Doctor. It's okay.
Yeah, we're okay, doctor. We just need some practice.
Okay.
Yeah.
Okay, that's good. Okay.
There's too much formula.
Yes. I'm sorry, but my slide cannot be used as summary formula. Oh, but this one is the one that I made myself, so I can share it with you. Do you want me to share it?
Yes, please.
Yes.
Yes.
Okay, so I will share the slides that I made, not the slides that belong to unit. So electric field, electric force, saya tak boleh share, but potential ni saya boleh share. Okay, so I'll be sharing that and uploading the video if you guys need to revise again. Other than that, have a great day. Take care. Don't forget to eat. Don't forget to take care of yourself. If you need anything, just WhatsApp me. Okay, bye-bye.
Thank you,
Thank you,
doctor.
doctor.
Welcome.
Thank you, doctor.
Don't forget to sign
Thank you,
in.
Doctor.
Welcome.
Thank you, doctor.
Welcome. Bye-bye.
Doctor,
Mm-hmm.
for the submission, we have assigned the latest one by this Saturday, right?
Uh-huh. Yang that
Boleh
let's pause dengan flux tu kan? This Saturday.
can I have an extension at least one day for that?
Sunday. You need until Sunday?
Mm-mm.
Okay. I think
Yeah,
I will
at
be
least.
granting everyone Sunday, good.
Yeah, for us.
All right. Sure.
Okay. Thank you, Doctor.
Welcome. Web assign. Is Divya okay? Doing okay? Nick, Nut Mango, Amirul Haziq, are you guys okay? Kita tidur tu. Web assign.
Just staying.
Just staying? Okay.